So thank you all for joining today. Today we at week chapter 5, which is text generation. Um, uh, and I will be here to lead the today discussion, though feel free to jump in because I'm newbie to this stuff. So yeah. Um, today's chapter is about text generation, and basically all the texts here are from the books because I have this soft copies. It is about text generation, and the types of text generation is basically text given some kind of prompt, which these texts are somehow indistinguishable what humans in some sense write, and this famous tools that give us very good text generation examples, OpenAI, GPT. And transformers basically because they are the brain behind GPT. These stuff, there are a lot of applications that do incredible stuff with text generation. One famous one is a conversational agent for Google Mina, and we can see that you can do some kind of story with that, and which is good. So the purpose of this chapter is to show how to use GPT for text generation and explore different coding strategies that have different effect of text generation. So one of the most important thing in text generation is the selection of the coding strategy you use, because that will have the impact of the text being generated. So this is the essence of this chapter. Two things to show how we can use Hugging Face Transformer GPT to text generation, and secondly, to explore a different kind of coding strategy to see which one works best and which one should be used in some certain situation, because some decoding strategies work best in some kind of different situation. So this is basically an example in the book where they give this as a prompt and it generate GPT-2, it generate a very coherent text. And this is one of the things we will see now, how this stuff have been generated. And the book discusses how text generation basically learns, how it tries to predict the next tokens, for example, based on the context, for example, this addition, also doing unscrambling, also via machine translation. So this is something we saw in the so now let's move on to the text generation. So the text generation, the book says other chapters that we have seen for classification sequence, they are basically simple in the sense that we just predict the probabilities of the next tokens, right? And now we just select the maximum agmax providers, use a softmax to select the highest probability and say this is the answer. But the problem with text generation is that when you have those kind of probabilities, you need to convert those probability text. So that's why they say converting the model probabilistic output to text require decoding. So in order in predicting the next text for sequence token classification and so forth, but for text generation, when you predict the probability, you need to decode that probability to text. So this decoding, that is where the challenge for text generation comes into. So number one is the challenge we have is it involves some kind of iterative. So for example, given this text, transformers are the, we need to predict the next probability and decode it to the text. So you can see we now decode the next. The first one is most. Now the next thing to generate the next one, you need to do the same stuff. So we can see that it is iterative stuff, right? You need to do some kind of iterative to generate the complete sense. So this is, it involves significant use of compute. So this is one of the stuff that deals with the generation. The number two is the quality and diversity of the generated text. So the quality of what is predicted and the diversity also is one of the challenges. So we'll see how these have been taken care. So these are I think the most important thing is the quality and diversity of the generated text depend on the choice of decoding method. So we have a couple of decoding methods. If you need diversity, so you need to choose a particular decoding method. But if you need quality, or you need some kind of quality, so you need to choose a particular decoding method, and we'll see those methods. So the first method the book explain is greedy search decoding. So as we said, the problem with text generation is when we predicted the tokens is what will be the next tokens here. We need to convert that probability to text, but changing that probability to text, that is the challenge. So this discuss about the decoding method. The first one is greedy search decoding. So greedy search decoding, as the name implies, is basically select the top probability. That is the one that with the highest probability. That's what the greedy search use. So we can see we can just apply the argmax and select the best one, which is basically similar to what we use choosing this step, the best one. So let's look at how we can use the GPT-2 to do text generation with this greedy search. So this is basically here we select the model saying GPT-2, and now we import it here, and now we use this, and now we train, and now we can have the input text that we wanted as a prompt to give to the model, and now we can provide the number of token, maybe. Yeah, so we just see 8 here. So here we can see we have the tokenizer, and now we have the maximum tokens that we gonna have, and now we run this, and now we can see that this is the input text, and now we can see that what it gives us is Transformers are the most popular toy line in the world, right? So this is basically, we can see that we use this using these simple lines to impute the first one, which is the highest one with the highest probability. So this is what we call greedy search, and it basically use select the one with top probabilities. But they also implement this decoding method, this greedy search. They implemented it here from scratch using alternative version, just to show us how greedy search works. So the same example I show using the implementation of Hugging Face Transformer, but this implementation manually, they show us, okay, now this is the text transformer at the, now what is the most probable next token? So we have most, only, and this is the choice. This is the probability 8.3, this is that. So we can see here, because we are using greedy method, it take the one with the highest probability. So we take this one, and now we add this one to the previous prompt. So you can see transformer add the, now we add it here, most, we add this one. So we just iterate adding to the prompt to see what will be predicted next, right? So this is just to show us how the greedy search really works. So just simple, take the highest probability. Let's look at still a story that sparks the OpenAI, which is from the paper of OpenAI, which is this the story of unicorn, which is the unicorn story. So we will take this context, which is basically from OpenAI paper about unicorn, and GPT-2 generate these guys. So we'll take this example and try to see whether we can have something similar to this. But before that, I mean, something that we can get may not relatively looks the same with the paper for the GPT-2. So this is the example, right? You can see the input text. You can see in a shocking, so this is that. And now we do the same thing as we saw. We just input the text and basically use the maximal length, and now select the greedy, the first one. So we can see this is what happened. But unfortunately, we can see that here there is some kind of repetitions here. the researchers from the university, the researchers were surprised to find the unicorn, were surprised to find the unicorn. So there is problem with greedy search, right? So one of the problem with the greedy search is that it gave kind of a repetitive sequence. So we can see here, give us repetitive sequence. So we basically, of course, need a better approach that can solve this issue of a repetitive sequence. And they discuss different alternative that can solve this issue. But we can see here, even this is repetitive. In some ways or in some sense, this repetition may work very well, like in a situation where you need factual answer or something that's really true. So this is what they said. Although greedy search decoding is really used for text generation tasks that require diversity, because we need to have diversity in this generated text. But here there is no diversity, right? Because it's just repeated. What they said is that it can be useful for producing short sequence of like arithmetics where deterministic and factually correct outputs is preferred. So this means that if I have an example, 5 plus 8 give me 13, 7 plus 2, 9. What about 1 plus 0? What will it give me? We know that this is factual. We need factual answer. So given this GPT-2 and try to run it, we can see that it generates factual answer, but there is no diversity, but it's so correct, right? So we can see here, we give it 5 plus 8, it gives us 13, 7 plus 2, it gives us 9. But what about 1 plus 0? It gives us 1. And now it predicts the next sequence, 1 plus 2, 2, 1 plus 7, So this is something that they clearly made mention that even though the greedy search, the greedy method does not have some kind of diversity, but is quite useful in this kind of where you need a deterministic and factually correct output. So yeah, so this is about the greedy method, greedy search. So anyone wants to add something before we move on or question? Okay, right. So no addition. Okay, so let's move on to beam search. So we can see basically that the greedy method is has some issue with that. So the alternative approach is to use what is called beam search decoding. So instead of taking the probable with highest probability at each step, we basically take the top most probable token, next tokens. So instead for us to take only one, so we take the top K or top B most probable text sequence, where we have this. So this is the example they gave. So here you can see you have the example transformer ID. So at each step, we are not taking the one, but we are producing some kind of given the B topmost and selecting it and outputting, and now until we generate the stop. And now we basically find the probability of all the sequence from here to here, from here to to the end, and find out which one has the probability that is higher than. So you can see like in the greedy search, it just predict the next token by best next token. But in the top K, what you use, we use a beam, we predict based on the B different kind of output, but we will not determine which one is the best unless we have everything. Now we make decision after finding the probability of all the sequence and find out which one is the best. So here you can see the next set of beams are chosen by considering all possible next tokens extension of the existing set and selecting the B most likely extension. The process is repeated until we reach the end. So the most likely sequence is selected by ranking the beams according to their log probability. So according to the log probabilities, then we select which path is the most quite often. So for example, look at this example that I saw here, comparison to greedy search. So here this is an example, a prompt, which say, hey, checking if you are back, let me know if you are around, and I'm keen to sync on how things are going. So this is the input, and the output says, I'm here, I'm here. It just gives him an answer, I'm here, and the sentence here. But this is, you can see that it's still predicting the next answer, right? But if we use this like beam search here, and another example here, you can see here we have different kind of answers. This is the input, and here you can see, yes, I'm back. I'm here, I'm coming soon, you can see different diversity. So you can see here, this is an example that is so like internet, like this is the email, and you can see Google is doing this kind of prediction. It gives you topmost, and you select which one, to predict. So you can see here, in this instance, it gives the base one, I'm here, using greedy search, I'm here, which is not probably the one if we take the sequence to find which one is the most probable. So you can see here taking, yes, I'm here, yes, I'm back. I may sound better than the I'm here, right? So this is what the beam search does. One thing also they discuss is that they don't actually, like in the previous one, in the beam search, we just take the probabilities. In the beam search, we take log probabilities instead of probabilities. So why calculating the probabilities, log probabilities? We can see that if we have the probability here, if it is long, we're gonna multiply the probabilities along the way, right? With this probability here, probability. Now multiplying by the product of probability to sum and find which way has the highest probability. The probability, because the probability is small, 0.00, it will lead to small probability, and now will lead to some kind of issue dealing with very small number. So this is what they discuss, that calculating overall probability of sequence involves calculating product of conditional probabilities. And each conditional probability is typically small number in the range of this. Taking their product can lead to small and overall probability that can easily underflow. Because we don't make decision which path we take unless we have everything. Now we find the product of probabilities. So this means that the computer can no longer precisely represent the result of the calculation. So if we can see an example, so let's assume that each path here has like 0.5 probability, and now multiplying the probability by, if we have tokens 1024, look at the number. So you can see this is very small number. So to avoid that, they use what we call log probability. So here you can see, instead of using taking mainly the probability, they take the log probability. So taking log probability will change this to summation problem, right? Because if you take the log, now it will take to sum. So you can see that summation, if we sum these guys, because we take the log probability, we sum them, so we will not have that issue of our probabilities getting smaller. And this is an example they show in the book, that running this guy by taking the sum, because this is log probability, this is what we have. So this is a number we can easily deal with, and unlike this very small number. So that's why they said here, finding the best path, we take the log probability and sum them along the way. And they said, okay, let's look at comparison of log probability or beam search and greedy search. So let's look at an example how greedy search works and the greedy search works. So we can see this one, the same example. We can calculate the log probability. So this is the same example we saw previously. Now they implement a kind of alpha function to implement log probability for at each step for each token. This is a log probability, and now the sequence of log probability. That is, at each step here we find the log probability, but now we can find the summation here, which is the helper function here, they implemented here, sequence log probability. So now if we want to do this, we can find the log probability now here of a model. So given the model now, I use this sequence log probability and now get the prediction. So you can see this is the output. Now this is a log probability, which is minus 67, right? And we can see that the results were separate. Yeah, this one also, it contains some repetition, right? To activate the beam search here, what we need to do is basically, oh, no, this is the greedy search. Yeah, this is the greedy search, not the beam one. So this is the greedy search. So here we have the log sequence probability of the greedy search, this one. For the beam search, what we need to do is basically to put the number of beam we want. If we need beam 3 or 4, we need to put the number of beam. And now we do the same thing as previous, and then we can see that here there is no kind of repetition, right? So we can see this is really better. So here we can see the greedy search has this kind of repetition, but the beam search don't have this. And we can say, so we can see that we get a better log probability, which is higher the beta with beam search than we did with the simple greedy. But beam search also has some issue. It does have some kind of repetition as well. Here I can see we don't have this repetition. Yeah, so you know, this stuff, they are sometimes stochastic and producing them, but what they said in the book is that the beam search also suffers that kind of repetitive test similar to greedy. So one way to remedy this issue is to introduce what we call n-gram penalty. So if we have a test, we try to predict, when we make sure that we see this n-gram, the discovery, then we will not generate this text. So here, this is how you provide that. You said no repeat n-gram size 3. So this means that it will not repeat any sequence with n-gram, 3 n-gram, that exact n-gram that had been seen and produced and been generated. So you can see here, this is the output, which is, I think, similar to the previous one, because this one also was quite good. So you can see, yeah, but we can see also this, the log probability also is, yeah. So the beam search here, n-gram, is good way to find trade-off between focusing on high probability tokens and reduce the repetition with n-gram. And it is commonly used in applications such as summarization and test translation. Yeah. So they also made mention that one factual correctness is less important than diversity of generated output. For example, in chart and you know, another alternative to reduce repetition while improving diversity is to use sampling. So we can see here, we basically strict that we want diversity, right? We want diversity. So using this beam search, but this is when we want to generate text that is basically maybe news or something. We want something to looks good, you know, to look human. But if we are doing something that may be less correct, it's just like we don't need the diversity. So we can use for maybe chit chat, we can use different method, which they suggest here, sampling method. So yeah, so anyone wants to add something before we move to the next method?
I have a question.
Yes.
So let's say you're outputting the maximum you can from a model, like a long text. This is pretty long, what you're doing here. And you set the beams to 5, right? Does anyone know the number of beams? So does that mean that it's fully parsing out 5 paths in the beam tree to the maximum number of tokens? Like the whole thing is being figured out at once, and then it chooses one of the 5 using the log probability, and then it just spits out that entire thing? Or is it actually some, like they're showing here, yeah, but or is it actually like chaining somehow? You know, where it does like 4 and then it does another beam search? Or is it really just sitting there and thinking through all the different beams and then spitting out the beam that is the best? Does anyone know?
Actually, I don't have the right answer.
I mean, the way they're showing it, it's just, and then the other question on it is, if you're specifying the number of beams, I mean, there's probably 1,000 options it could take. So how is it, you know, there's 1,000 paths for this tree. How is it just taking 5 when it doesn't know where it's going, you know, like without parsing everyone out? You know what I mean? How is it making that decision?
Yeah, so it's the same as the greedy search, but it's taking the top B, you know. So when you said your you have the 5 beam search. So it's taking the top B most probable next tokens, where B is the beam. So I don't know if that's the question you are trying to ask.
Well, sure, but it's interesting because the next word, unless you look 5 words down the path, even if you like have a cutoff and say, well, the first word you predict, so you've got the word transformers, right? Let's just say the first word you're predicting is R, or is that, that second column there. So the first column is transformers in it. The second one is R, will, have.
Yep.
So I could see putting, maybe there's a threshold, but if you put a threshold on the probability and it's got to be above whatever, you're discounting a bunch of opportunities, which might actually turn out to be the better word when you look. The point of the beam search is you're looking all the way down there, to see really. So it may be the second word. So anyway, I'm just asking more detail than they're giving in the book, I think. Yeah.
Then I think the way it works, as I understand it, and I can show you the example that they present from the Stanford NLP class, and the way I understand it and the way they explain it there is, let's say we stick to, instead of 5, let's say we just stick to 2. So at each point, meaning at each stage of this tree, it generates 2 choices. Then it calculates the log probability up to that point, and then chooses for the 2 parts that have the highest probability. It predicts 2 choices again, calculates the highest 2 probability paths until that point, and keeps proceeding that way.
Okay, so it is an iterative log probability sort of thing. It's like when it keeps getting more words, and the calculation just keeps getting a little longer.
Right, and does it again and again at every stage. So at every stage, and sometimes the stages can end earlier, for example, right? I mean, it stops generating because they're in further. But in the example they share, it's for translation, but the same principle applies here as well. So it calculates the log probability to each stage and then predicts the top 5, as Sansadin was saying. Let's say if we stick with 5, then it calculates the log probability to that point and only chooses the 5 paths that are highest probability up to that point and generates 5 new choices again.
So these models have a, like OpenAI, their playground and their API, they limit the number of total tokens for the prompt and the response, okay? But it looks to me like from beam search, you could actually just go forever. But I guess at some point, so why do anyone understand why there is a total character limit like that on the input plus the output? And is it related to beam search?
That's related to the model. The point is, like I said, when you create the next word, for instance, if you create the toy, how do you create the toy? You have toy and toys and toys, okay? How do you create this? The model has to read the whole sentence from so far. Transformers are the most popular, and then given that input, what should be the next point? So the longer your text becomes, the more work does the underlying model have to do for each following on step. So the beam search is sort of the beam search part of it. The search part is cheap, but the prediction of the next step becomes more and more expensive as you go on.
Okay, yeah, that makes sense because you're incorporating more and more words and your input, your prompt, and your prompt becomes longer and longer. So a couple things have been answered. One is, yes, it does completely parse out the entire tree, number of paths you select, and then it just spits it all out at once. So when you're sitting there, so when I'm sitting there waiting in the playground or whatever, the response takes time because it's continually putting in the prompt that's getting longer and longer, and then it's doing beam search, and it's actually doing that for different prompts, right? So it's not just putting in one prompt when you're doing beam search, right? It's got to be putting in one prompt with this word at the end of it and one prompt with that word at the end of it, going along with stream devices two number of beams. So there's a lot of, so it's, you're actually calling the model when you have two beams twice at each step.
Exactly.
Okay.
And if you have 10 beams, then you would at each step sort of, if you would have infinite amount of beams, you would have a tree which is growing exponentially. So if you have one word, then you have say two words and 4 words and 6, 8 words and so on. If you have a beam, you just you cut that you say, if you have more solutions then I want to have beams, I throw away all the solution except the top n. But then you sort of, if you say to have 10 beams, at each step you take the 10 best old one, compute the next one, and it takes the 10 best which are there as a prompt for the next time. So you have sort of, for each step you produce run the model 10 times.
Yeah. But my point is that this is going to seriously affect performance, whether how many beams you choose, because that's how many prompts you have to put in, and the prompts are, it's not quick. These models are not fast, and so the beams must seriously affect. And I don't think in OpenAI they give you a choice of selecting how many beams you get in your beam search, and that's probably one of the reasons that they don't do that, because you just grind the model to a halt basically. So why does
do they allow you to select the the playground? Do they allow you to select the decoding strategy?
No, not as far as I know. They have a top P, which is talked about in the book, the nucleus sampling, but no, there's not. So
maybe
it's
maybe the playground is not using beam search, is using top T, as we can see one of the decoding strategy, which is top K, something like that.
No, it's probably using the best. It's using whatever the best thing is out there, because it's absolutely amazing. The instruct model and on the playground, it's ridiculous. It's a new world. But yeah, it's good. Maybe I'll look up what they're using under the hood now that I understand a little bit more about the iterative nature of beam search and how you have to, if you're actually submitting one prompt per beam branch, that's a lot of prompts to be running in the background.
Cool. Right. Okay, so now we have seen now two decoding strategies, which is the first one, greedy, which select base probabilities, and the beam search, which use different strategy. But the beam search, as you can see, produce a coherent test, which is correct. But when you need diversity of them, is less important. You can use another method, which is called sampling method. So that's why you see, and the video they say, selecting the decoding method depends on your application, on what you want to do. So the next one is sampling method, which basically we can see that sampling method will reduce repetition and improve diversity, because you are just sampling, right? So if you have random stuff, you just sample, probably you can reduce the repetition, and you can do some stuff. So basically, just applying a softmax to our log probabilities and do these, select the top one. We can easily control the diversity by adding outputting it, by adding what is called a temperature parameter that scale the logic before taking softmax. So here you can see before taking the softmax, you basically adding another parameter, temperature. We will see it in the how we can use that. So yeah, so we can see the effect of the temperature here. We can see that when you have temperature less than 1 and when you have temperature greater than 1. So we can see here, the book says that if you have, this is the probabilities, sort of the sorted tokens probability. And this one is probability t equals 0.1, t equals 1, t equals 2. And now we can see this is the stored tokens. So we can see here when t less than 1, the distribution become fixed around the origin and real token are suppressed. So we can see that when t equals 1, this one become fixed and the real token are suppressed. So it means that real token are suppressed. They are not. They don't. They have they are separate, they don't have higher probabilities. And when T is greater than 1, the distribution flattens out and each token becomes equally likely. And when you have T, the temperature is larger, then the distribution flattens here like this, and now the tokens will have like the same probabilities. So it will be producing some garbage because it's not telling us which one is having highest probability. So in a nutshell, when we want to see, when we want to train the model using sampling, we said, okay, give all the sampling, but use this temperature, right? And you can see we say do sample, we activate to do sampling. So with this argument, and we provide the temperature. So the temperature depends. Here we can see we provide the temperature equals to 0, 2, but this top K is explained next. The temperature here is 2, and we can see here that it gives us the text generated is not related to basically what we talk about. It's not related to the prompt, which give us the garbage, right? Because the temperature, because as we can see here, the more you increase the temperature, it gives you nearly equal probabilities among all the tokens, and it will just select any probability because this is sampling. It will select anyone randomly. We can clearly see the high temperature has produced mostly gibberish. So what we can do is we can change the temperature 0.2, right? And now we can see selecting the temperature give us, you can see something which looks like related to the prompt about the unicorn, and you can see that. So here we can see that selecting low temperature allow us to control the quality of the sample, and selecting the higher temperature produce garbage. So this is sampling method, but there is also a trade-off they discuss about the coherence. So here we can see low temperature in the sampling strategy give us something coherent, which we expect, and diversity, which is high temperature. So here we can see when we have high temperature, it gives us something diversity, but there is no coherence. So we need to find some kind of trade-off. How can we trade off of using this?
1 second. Isn't that text extremely repetitive? Sort of the if you read the text over there, it seems the researchers from the University of California, Los Angeles, discovered. And the Andes mountains is repeated. I think it's worse. Maybe it's worse than the really. Now it looks good.
I mean, that's the essence, like having the smaller temperature. I think I can. Oh, I mean, yeah. I mean, you know, these things. So you can see, this one is not as bad as previous, right?
That's good.
Yeah. So changing, reducing the temperature makes the generation more coherent, right? And yeah.
If you take temperature equal to 0, you go back to the greedy strategy of only taking the top one.
Yes. So let's look at it. I don't know. Let's look at. I think. Oh no.
Maybe you have 0.001 or something like this.
Oh yeah. Oh, look at that. Anyway, the temperature determine how, you know, I think so. Tuning, this is a parameter tuning, you know, but how do we select the best temperature? I think this will be an art, you know, finding, you know, I don't know, like, yeah. So, yeah. So there is trade-off between coherence and diversity. So when we use low temperature, we have coherence, but when we use higher temperature, we achieve diversity. So how can we achieve this trade-off? So to achieve this trade-off is what we call to truncate distribution of the vocabulary, which will be discussed as top K and nucleus sampling. So what means is that we basically try to truncate or remove some vocabulary from our distribution. This allows us to adjust diversity freely with temperature, but a more limited range that exclude words that are too strange with low probability. So there are two main approaches. So to sum up, this sampling method works well, and there are two things. Using temperature allow us to have a very coherent system, but using high temperature allow us to achieve more diversity, which is not coherent. But how can we achieve these two trade-off to have a coherent and more also diverse? They said we can use what is called top K and nucleus nucleus. So what is top K? Basically extension of using temperature. So extension of using temperature to achieve what we discussed about that trade-off. So you can see they said it's just extension of using temperature. The basic idea is to restrict the number of possible tokens we can sample from each time step. So you can see here is that the basic idea is just we restrict the number of sampling that we're going to use. Yeah, so we can look at this cumulative probability distribution of the model at t equals to 1. So we can see here that basically that the count of the tokens we have, we can see the probabilities here maybe, which is so small, 10 to 9, 10 to 8, they have higher count, but we can see with higher probability, we can see like we have this small number of something that is maybe the diversity is small. So we can see like when we have, I think this is the higher probability. So when we have higher probability, the count, the possible stuff you're gonna have maybe are small. But when you have, this is large probability, right? This is small. Okay, yeah. So when you have this small probability, then you have some kind of rubbish. You can have very large number of possible selection tokens to take. So the issue is that if we sample hundreds of times, there is a significant chance of picking an unlikely token at some point. So because you can see that if we have large sample, because like if we use this, we have large sample, then we can basically select samples that do not contribute largely to that. So this is the idea of top K sampling, that where we basically avoid low probability. This is low probability. So all these ones with the low probability, because we have the count we have, they are large. So you can see the pool you are going to do the selections is very large, which you can select something rubbish. But when you have higher probability, you're gonna have, you can see, you're gonna have a very small pool that you're gonna select the tokens, right? So this is the top K sampling. The idea behind it is to avoid low probability choices by only sampling from the top K tokens with the highest probability. So we're gonna select something with the high from this one, top K, top ones with the highest probability. So this is the idea. So since we said that this is something similar to extension of the other method, so here the something that we have been seeing is just to provide this argument top K 50. So and we can see here we just call this guy, and now we tell us give this one, and now we do sampling. It's still the something with sampling because it's something, and we can see here we have this. So with this top K sample, they said this is arguably the most human looking text we have been generated. So we can see here the wild unicorn. So this looks like the one that generated from OpenAI example in the paper. This looks so this means that the top K sample, I think from this way is the one that best used, maybe even in the playground that Dari was talking about in the OpenAI. I'm not sure anyway, but from here we can see that using top K provide better performance. Anyone want to add something here?
What I can see over here, it's faster than the beam search, because in beam search, as we said, we have 10 times or whatever the number of beams you have. Over here, just take one result each time that's fast. And if they say it's high quality or it looks human-like, then that's good in both performance and perceived quality.
Yeah. Okay, cool.
The one other comment I would add is that in both cases, it's actually collecting kind of, I mean, the way to think about it is in top K, it says, or we say, choose the highest probability 50 tokens. So we let the total probability of the choices of the 50 tokens to vary because it chooses the top high probable but limited to 50 tokens. So 50 tokens put together, token 1 would be 0.1, token 2 could be 0.2, token 3 could be 0.3, so on. And it accumulates that, and the P, the probability, could be whatever the sum of the 50 tokens probability is. Now, as compared to this next technique we'll see, which is top P, there we cut it off from the probability bound and say whatever number of tokens lie within this probability, randomly pick from them. So that's why one is limiting it from the number of tokens and giving it the number, saying choose 10 of the highest probability tokens. So it goes, I've chosen 1, I've chosen 2, I've chosen 3, and when I reach 10, I'm done, regardless of what the total probability of those top 10 tokens is. And then in the other instance, you flip it around and you say, I don't care about the number of tokens, but I care about the probability that I'm going to cut you off at, so that when you get to this given probability, if you have 5 tokens, cut it off right there. I don't let you go below that probability. So that then limits the choice from the view of probability. But so there, in that case, you don't allow you allow the number to vary, not the total probability. In this case, you allow the probability to vary, the total probability to vary, but you specify the number. So that's how you get the choice between top K, or what they call nucleus, or top P.
Maybe I just would want to add to that explanation that both of these approaches have their own extreme cases where they can fail. So if you say you have a fixed number, so you say you take top 50, and it could be that you have only, say, 10 words which really make sense. Sort of, you have continuation of 10 words which really make sense, and then you just have very low probabilities for the next 40 words. Then it would include 30 or 40 really rubbish words of a very, very low probability, but they still would be included and sometimes be used. So, but if you would fix the probability, you could say, I only include words which make sense, and anything which is meaningless will not be included. So this would be an advantage of fixing the probability, but not the number of words. But on the other hand, if you fix a probability and you have no word which matches this gap, if you say the first word which you have has a lower probability than your threshold, then basically your algorithm would stop and says, I don't find any word how to continue. It's very unlikely how to continue over here. So both of these points have their own failure approaches. Maybe you want to combine them, or you're happy with how they fail and you say, well, if there's no probable continuations, then don't continue.
Right.
So
right. Okay. So good one. So yeah. So one thing is, how do we choose K? The value of K is chosen manually, and the same for each choice in the question. I think the next one, which is they talk about, is top P, the Sylvanus is talking about, is solve the issue. We have the problem with top K sampling. One common concerns through top K sampling is that it does not dynamically adapt the number of words that are filtered from the next word probability distribution in each step. So I actually, maybe somebody can explain again the top P, because this is, I rushed this, I was putting this slide now in the last minute, and this one I cannot explain how is this top P? So even as you just explained, can you explain again how top P
Sure.
works? Okay.
Yeah, sure. So what I'm saying is in top K, you say that give me, and I'm going to use a different number than 50, but let's say give me the top or when the top means the highest probability, but 10 words. So start with the, the greedy search word will obviously come first because that's the highest probability word. Then choose the next highest probability word, then the next highest probability word. Like that, you go down the list and choose 10 words from the highest probability to the next highest probability to the third highest probability to the fourth highest probability. And like that, you choose 10 words which have the 10 highest probability. Okay. And you allow the summation of the probabilities. Like let's say each one, to keep it simple, the highest probability is 0.1. The next one is, let's say, the next lower one is 0.09 and then 0.08 and so on. So think of it as the top 10 means that you would add 0.1 plus 0.09 plus 0.08 plus 0.07 and so on. Now, on the other hand, in case of top P, what you decide is that I'm going to cut you off at probability 0.37. Let's say I'm just randomly picking a number, and then give me the words that are above that cutoff in probability. So now you allow the words number to vary. So because you're cutting it off at, let's say, 0.37, in the example I was saying earlier, you would allow 0.1, you would allow 0.9, you would 0.09, you would allow 0.08, but whenever you get to 0.37, you cut it off.
Oh, okay.
Right? So the number of words in the top P choice will vary, but the probability cutoff is strong. And that's where also what Yakov was mentioning earlier, if none of the words in the top K, if you allow, too big, like 50 words, like you were saying in the example, the top 10 may be relevant, but 40 may not be because you allow all lower probability words to get in. On the other hand, in case of top P, you might cut it off so high that no words are found which are higher probability, because the highest probability word at that point may be a very low probability word in terms of actual probability. So if you choose your cutoff to be very high in that case, as Yakov was explaining, you may find no words fit into a cutoff of, let's say, 0.5, for example. But that's the choice between top K and top P.
Yeah, I think the idea that if you have a threshold and you get nothing back, it's probably good to shut up at that point, right? Unless you're drunk, right? So, so actually the idea of getting nothing because you have a high threshold is probably pretty good. Unless you want a drunk model. Low probable things, which is fun, maybe.
Actually, I thought about shutting off about that, but as I read now the text over here, I think they do something else. They're not saying that you look at each word and you say, if that word is not likely, then I don't include it. But they say we take the top 95% of the total words which are there. So if you have a total bucket of 100%, and so you have the first words take up some of the 100%, like first word takes 30%. I just make extreme numbers in order to make things smaller. So I have 30% the first word, the second word 20%. So we have already a total of 50%. Then let's say 10% and 5%. So the first words take up some space, and then you have the long tail, which takes many more, takes up the rest. So if you say we take the 95%, so we take all the words except for the 5% which have the lower probabilities. So according to that explanation, we actually don't shut up, because there will always be some words within the first part of 90%.
So you're saying, so which one is it? Is it top, is it is it top proportion like you were just explaining, Jakob, or is it really just a probability threshold?
I just checked it in the book. This is what it's saying. So if you look at page 138, and then at the very bottom, at the last two lines, and go on to page 180, 109,
We said a
39.
condition in which and when to cut off. This condition is when a certain probability mass, whatever that means, I think that's proportion, is
the sum of the words which are selected.
The sum of the probability of the words that, so the first word, like as I was explaining, could have a probability of 0.3. The next, if you give it a cutoff, or, you know, when I say, or very high probability. So, but if you give a 0.9 cutoff, then as soon as your summation of the word probability reaches that, that's it.
So it's not a proportion of the possibilities.
No, it's not a proportion. It's a cumulative probabilities of each.
So it
word
is a threshold.
choice.
It really literally is a threshold. It's just from the cumulative.
But it's not a threshold per word. It's a threshold where you stop looking for more words.
Yeah.
So if your words have all a very low probability, then you will take a lot of them to make up that chunk. So if you, I'm saying that if you have very high probable words, like a very strong head, and then you have a long tail, you will take only the strong head because it already eats up that allocation. But if your words are all a very low probability, you take a lot of them.
Yeah, it's a probability. It's a cumulative probability threshold. That's the way to think about it.
And actually, we get the opposite result. So if you would say a threshold for each word, then if the words are unlikely, then the problem should stop, shut up. But over here, if the words are very unlikely, then it actually will allow a lot of them, and to choose from all the unlikely words. What's that? Sort of the characteristic is opposite what we just explained before.
So, Sylvanus, your first explanation of top P, a bit is correct, right? Because that's what I have on top of my mind now, because I understand it. But I think Jakob is saying something different, if I'm right. Is that correct?
No, it's the same thing.
I explained top P wrong, and then I looked in the book and I saw that the book does something else, and so I explained that. So I was re-explaining what people were saying before, or I misunderstood something, and then I explain again. Now top P is equal to 90%. It doesn't make sense because almost all tokens will be much below.
Yes.
You can only have one token which is 90%. So over here top P means until you eat up those tokens which you take, eat up 90%.
Yeah. Okay. Yeah. Because I thank you, Sylvanus, because I understand the explanation. So like I was like trying. Oh, I didn't understand. So thank you very much for that. So we can see that top P sampling also has produced a coherent story. So, but now can you combine top K and top P sampling? It is yes. So we can combine these two sampling approach to get the best of the world, right? So here we can say, okay. We can provide the top P, and we can provide the top, is it top K, right? Yep, we can provide that. We can provide, maybe let me say, I provided 0 here, I think. I don't know why, but it.
You want 50, I think.
Yeah, maybe let's see something like this. Yes. So you can see here, we provide the two, this guy and this guy, and we can see the sample out. We take the first one here, which is also coherent as well, right? And you can see it even give us where the research was carried out, which is yeah. So finally, which decoding method are we going to use? So there is no universally best method, which depend on your nature of the task you are doing to generate text. If your model want to perform precise tasks like arithmetic, which factual answer you need, then methods such as greedy method can work, right? As we saw, it can do mathematics. But if you want to generate a model with longer tail and even be creative, then you should switch to sampling method and increase the temperature and or use mixed top K and mixed nucleus as we saw. So finally, we can see that using temperature give us, as we saw, better also result. And now using sampling method with top K, which is extension of using sampling method, which are top K and nucleus, are also produce better result. Right. So that's what I have today. Thank you very much. Anyone wants to add something? Yeah. So I think today we have David. David, you also show interest to present one chapter, right? Thank you for volunteering. I think in a couple of weeks we will have the chapter you selected. I think you selected one chapter, which is basically what is that? Making transformer efficient in production. But unfortunately, the next week we have chapter 6. We don't have the presenter, so anybody can volunteer. We have summarization, chapter 6. I'm not sure if anyone here can volunteer to present the next chapter, which is summarization. Okay, so maybe we can discuss in the Slack channel to find a presenter, a volunteer for the next chapter. Yeah, so anyone wants to ask something before we go?
I want to say thank you very much. Thank you. Your presentation was very clear, and it was sort of very pleasant to hear.
Okay, thank you very much. Yeah, thank you. So thank you all for contributing and for the discussion. And I would like to see somebody to volunteer chapter 6 for next week. And thank you all for joining, and see your faces next week. Thank you very much. Thank you. Ciao, ciao. Bye.
Alrighty, bye.
Bye.